Just one second. All right, so let's begin. Hello everyone, I am Srishi Siddharth. I am a TA for this course, State Space Approach to Control System Analysis and Design. Welcome to 6 weeks tutorial session. So let's begin by recalling the concepts that were done in 6 weeks lectures. So let's recall. Okay, so the main theme was pole placement technique. So we are going to look at various methods on how to place the poles at desired locations. So pole placement techniques. So the first one was pole placement using the desired characteristic equation. Next, there were two techniques. So I write down the names. This is the Ackermann's formula. Same. Then, if the system is not completely controllable, then we can transform it into a standard form for uncontrollable system and then design the pole placement control. So in that case, the unstable eigenvalue should be stabilizable, right? So this is the pole placement technique. So I'll just write this down, right? Pole placement for stabilizable systems. We have another pole placement technique by converting into the CCF form. So pole placement by transforming the system with the controllable canonical form or the first companion form. So let's begin with the question. Okay, so we are going to deal with LTI systems. So X short is AX plus BU, and the output is CX plus DU. There are n states for the system. So X is in RE. So if we assume all states, sorry, that all the n states x1 to xn can be accurately measured so that we can form a feedback law, can be accurately measured at all times. It is possible to implement a linear control. So it's linear in the states to implement a linear control of the form minus k1 x1 till minus kn xn. So the coefficients k are independent of time. So if you have to write this down in a vector notation, this would be minus the row vector k1 to kn times the column vector x. This is x1, x2 till x. This can be written as q equals minus kx. So if x is n by 1 column vector, k is going to be n by 1 row vector. Sorry, this is going to be 1 by n. This is known as the gain matrix, gain vector, or the control gain vector. So let's substitute this form of u in the LTI system. This is going to be x dot equals ax plus b times minus kx. Now this is a differential equation without input because we have already substituted the input. So if we want that x should converge to 0 as time t tends to infinity, then a minus bk should be Hertz. Negative real parts. So A minus Bk is also known as the closed loop A matrix, ACL. And the solution to this closed loop system is going to be xt equals e to the power A minus Bkt x at time 0. So now the question is how to select the vector k. So if we know that the desired eigenvalues have to be at certain locations in the S-plane. So this is the S-plane with imaginary and real axis. And for example, we want it to be at minus 1, minus 5. So the characteristic equation of the closed loop system should look like this, right? And this is going to be s squared plus xs plus 5. So we'll compare this with the desired characteristic equation. We'll compare this with the this equation for a minus bk. And by comparing the two equations, we will obtain the unknown values of k. So the desired characteristic equation of the closed loop system is it's going to be determinant of a minus bk, say minus si or lambda I equals 0. Desired eigenvalues. There are going to be n desired eigenvalues for a nth order system. Desired eigenvalues are located at till lambda n. So lambda I can be real or complex conjugate pair. So the desired characteristic equation is going to be s minus lambda 1, s minus lambda 2. And compare 1 and 2 to find out the value of k. Okay, so let's look at a second order system. X dot equals 0, 1, 0, 0. Plus 0, 1, 3. So the system is a second order integrator where x1 dot is x2 and x2 dot is simply u. Now let's compute the eigenvalues of the system without any input. So this is going to be determinant of a minus lambda I equals 0. So this is minus lambda minus lambda minus 0. Sorry about this. There was some network issue from my end. All right. So the system's eigenvalues are at 0, 0. So the system eigenvalues GP on the imaginary axis, then the system is unstable, right? So we have to introduce U so that the system becomes stable. And for that, the eigenvalues of the closed loop system should be on the left hand side of the SP. Okay. So let's say that U in this case is going to be minus K1, K2 times X1, X2. The unknowns, closed loop system, X dot equals A minus BK times U, sorry, X. So let's calculate A minus BK to be 0, 1, 0, 0 minus 0, 1, K1, K2. So 0, 0, K1, K2. And what's the characteristic equation of the closed loop system? This is A minus BK minus SI equals 0. So let's complete this. It's going to be minus S minus K2 minus S. So this implies that we have minus S times minus K2 minus S plus K1 equals 0. This is S plus K2 this is the characteristic equation. The same is as well. Now we have to select some eigenvalues. So let's say that we have been given some design specification. And this is a second order system. So design specification can be in terms of settling time or peak overshoot. What is the explain? For some design specification, we might have eigenvalues on the real axis on the negative half plane or as complex conjugate bits. So this is S square plus zeta omega n plus omega n equals 0. So let me know if this is correct. This is the standard second order characteristic equation in terms of natural frequency and the damping ratio. So depending on overshoot, settling time, and any other parameters, This would give us what zeta and omega n should be. This might be omega square, I think. And we can substitute this way to get the desired characteristic equation. Another way is that which we saw earlier, we have exact position of eigenvalues in equation 2 and we can just form the desired characteristic equation. Alright, so let's say that we have been given that lambda 1 and lambda 2 are complex. Therefore, they should be in complex conjugate pair. The desired characteristic equation is x plus 4 minus j4 . So let's expand this. This is correct. So this is going to be equation 2. So I'm comparing 1 and 2. Let's see. S square has coefficient 1. Then K2 is 8 and K1 is 32. So the feedback control law, which is linear in this state, is going to be minus 32 8 times S1 extra. This is K. So you can also verify. So how to verify that you have indeed got the K, which places the eigenvalues at these locations? You have A minus BK, right? So K is there, you have A minus BK to compute the eigenvalues. Right? They're equal to the desired eigenvalues. So I hope that this was clear to you. Let's move on to the next question. Just a second. So let's look at a few multiple choice questions. We have four options. A is remains the same. So let me know what the answer is. So you can either unmute yourself or write in the chat box. Mm, So you can look at it by writing down the time constant for a second order system. So that is simply, for this T, you can write it out star or any other symbol of use. So this on the S plane, sorry, this is zeta omega n. Zeta omega n is the real part of the root of the characteristic equation, right? Plus the damping. So if the time con, alright, so if the eigenvalue of the pole is further apart in the S plane, here for example zeta omega n, then the time constant of the system is going to be lower. This means that the system is going to decay to zero faster. So the time constant of the system decreases as we move the pole farther away from the origin. Okay. Let's look at another question. We are going to solve this question using the comparison between the characteristic equation of the closed loop system and the desired one. And after this, we will also apply the Ackermann's formula and see what we get. This is find the controller parameters. System. This is x dot equals 1, 1, 1, 2. Poles are desired to be located at s equals -2 and -1. Okay, so let's write down the desired characteristic equation. This is going to be easy. In this case, this is s plus 2, s plus 1 equals 0. So we have s square plus s plus 2s plus 2 equals 0. This is equation 1. So we have two states. We will have K1 and K2. In this case, K1, K2 is going to be on the first row. So this 1, 1, 1, 2. Then we compute the characteristic equation of the closed loop system. So let's see, this is going to be 1 minus K1 minus S, 2 minus S, minus K2 and 1. So we have 2 times 1 minus K1 is 2S plus S squared. So we have S squared plus S and minus K1 plus 2. Then we have twice of 1 minus K1 plus 0. This is going to be 2 minus 1. So I'm comparing both the equations. First one is we get 3 equals. So minus 3. Let me check this one. K1 equals 6. And the other equation is 1 minus 2K1 plus K2 equals 2. So let's substitute K1 equals 6. So the gain vector K is 6 and 13. This was about placing the eigenvalues at the desired location using the desired characteristic equation. Now let's look at a question in which we employ the first companion form to place the ports at the desired location. This is question 3. Do the first companion form. So the A matrix for the system is 6, 4, 1, minus 5, minus 4, 0, 0, minus 3, minus 1. And V is 1, 0, 0. Now I'm using the first companion form. And K such that the eigenvalues of A plus BK is 1, minus 1, and minus 1. So note that we can either consider A minus BK or A plus BK depending on U, right? So we can consider if U is minus KX, this means that the closed loop system is x dot equals A minus BKX. If we say that the control is KX, then it's x dot equals A plus BK. You can choose either of these two formulations. Alright, so let's begin. So to convert to the first companion form, we need the controllability matrices. So for a third order system, it's going to be A squared C, B, A, B, and A squared B. So AB is it's going to be 6 minus 5 and 0. And then A squared B is going to be 36 minus 20, 50. Let me know if there are any mistakes with the calculations. So in this case, C is going to be 1, 0, 0. This is a square matrix of size 3 by 3. To check the rank of this matrix, we can simply compute the determinant. This is 1, 0. This implies that the pair AB is controllable. this is rank of C is 3. Alright. Now we have to find the transformation which transforms the system AD to the first component form. So we'll do that by using the controllability matrix. So to find the similarity transformation, we must choose C as follows. So if it's a third order system and we want a transformation which takes us from X to Z, then T should be invertible, right? And this means that T should be a square matrix of size 3 by 3. Okay. So I'm going to write down the transformation matrix as C, and C looks like alpha 1, alpha 3. Are 3 by 1 column vectors. So alpha 1 should be chosen. We'll see how it is. So C operating on the first column of the controllability matrix should be 0. So what do we get? We get alpha 1, alpha 2, alpha 3 times the first column is B. So this is 1, 0, 0. Simply implies that alpha 1 should be 0. So just to note, we use C to obtain the transformation matrix T. So C times the second column of the controllability matrix should be 0. This means we have alpha 1, alpha 2, alpha 3. We have alpha 1 equals 0. So let's substitute that. So the second column of C is 6 minus 5, 0. Yes, minus 5 alpha 2 equals 0, which is alpha 2 equals 0. And then we have that the controllability matrix times the last column, sorry, C times the last column of controllability matrix should be 1. Okay. So we have 0, 0 and alpha 3. It's 16 minus 50 and 50, which implies that alpha 3 is 1 over 50. Yes. So C is 0, 0, 1 over 50. So the transformation denoted by a T that transforms clear TB into the first companion plant. Is T equals C. So note that this C is not from the system properties, right? Because maybe this is ABCD. Till for general system, it is just C e to the power n minus 1. And for our case, this is C C A square. So let's compute this. And 641 0 0 sorry 0 minus 1 by 5 plus 1 over 50. Then you can get CA square as well. This is 1 and 1 over 50. So let's substitute in T. T is 0 0 1 over 50. So just 1 second. So this is 0 0 1 over 50. 1 0 minus 1 by 5 minus 1 over 50. 1 1 and 1 over 50. So the first check should be is T invertible. So how do you do that? You check the determinant of T. So we can expand along the first column and simply get 1 times 1 by 5 into 1 by 50. Therefore, T is invertible. Now, since it is a 3 by 3 matrix, you can use any of the formulas to get the inverse of the matrix. So I write down the matrix T inverse directly. You can just verify this later. This is going to be 4, 5, 1, minus 5, minus 5, 0, 14.9925, 0, 0. So if we have used the transformation T in the controllable canonical form, this is given us. So let's say that the new state was Y. Let's say it was Z, which we did earlier. So this is going to be Z dot T equals AC times ZT plus BC times UT. So ZT is T times X of T. So we can get what should be the differential equation for Z, right? Z dot is Tx dot, which is Tax plus Tbu. In terms of Z, this is going to be, so this is the matrix AC, this is BC. We have the matrix A, T and T inverse. We get AC as 0, 1, 0.0005. Yeah. So you can approximately write this as 0.10.0.001 minus 19, 6 and 1. So this is the first companion form, right? We have a chain of integrators in the second last state. And in the last row, we have minus negative of the coefficients of the transfer function. So let's write BC also, which is T times B. And in the first companion form, it should come out to be exactly 0.001. This is 0.001. So you should check the calculations if you get this. So in the general form, first companion form for the third order system, it should look like 0.10.0.001, alpha 1, alpha 2, alpha 3. So the advantage of using or transforming the system to the first companion form is we can now simply get A minus BK. So AC minus BCK is simply 0.10.0.001. Alpha 1 minus K1, alpha 2 minus K2, alpha 3 minus K3. So then this was A plus BK, right? So AC plus BCK is plus. So for any nth order system, if we have transformed the system to the first companion form, simply get this as the closed loop matrix. This is alpha 1 plus K1, alpha 2 plus K2, till alpha n plus K. Alright. Here's one more advantage that we simply get the closed loop characteristic equation as so this is simply S cube minus alpha 3 plus K3 S square. So negative. So we will plus alpha 2 plus K2S minus alpha 1 plus K1 equals 0. So we know alpha 1, alpha 2 and alpha 3. So let's substitute them. This is S cube minus minus 19 plus K1 equals 0. We also have the desired eigenvalue, so we can compute the desired characteristic quotient. S plus 1 cube equals 0. So this is S cube plus 3s square plus 3s plus 1 equals 8. Let's compare the two equations. Okay, we have minus 1 plus 8, 3 equals 3, which implies Q3 is minus 4. Of minus 6 plus K2 equals 3, K2 is minus 9. Finally, we have uh, minus 19 plus K1 equals 1, sorry, minus 1, K1 equals 18. So the gain vector looks like 18 minus 9 minus 4. So let's observe that u is now going to be k times x. Is this true? That is, if we substitute u as k times x, we get the desired eigenvalues of this closed loop system. So it is a plus pk have lambda as minus 1 minus 1 minus 1. So it's no, right? Because we have actually found out the feedback vector k for the transform system. It's for the state z. So that's because we have computed k for z dot equals acz plus bc. So how should we transform u so that it becomes the control vector for the original system? Okay, so let's see. We have x equals t inverse z, right? So x dot is t inverse z dot. This is t inverse AC times z plus BC times u. So z is tx, t inverse BC times u. We have u equals kz, right? Okay, so this is going to be 3 t times z. So to just write it in simply, we have u equals kz. Z can be written as t times x. So the control gain for x dot equals x plus du. So control gain for the original system is k times t. Let's stop here and say that the CCF form of the system should have this k, and if we want to apply it to the original system, we should multiply by t. So verify a plus b times kt desired eigenvalues. So I think in this question we were asked to find the gain such that the CCF form has these eigenvalues. Yeah. This is fine. We transform the system to the first companion form. But the eigenvalues of the original system, A plus BK, should be at -1, -1, -1. So just check whether these eigenvalues are at. Okay, just a second. So check if AC plus BCK has. So this is fine. Let's move on to the next question of placing the poles at the desired location for a stabilizable system. So this is question 4. So since we are talking about formulating a control signal, we just need A and B, right? So A is -130, -1, -4, 1, 0, -3, -1. B is 1, 0, -1. First one is the pair AB controllable? Show that the pair AB is stabilizable. A plus BK plus the vibrates matrix. Okay, so for A, we just need to find the controllability matrix, right? So let's do that. C is going to be B AB A square B. So AB is -130 -1 -1 and simply 1. Square B is A times AB. In this case, we have 1 minus 6, then 1 plus 3, and 6. This is going to be 6 minus 1. This is minus 5. This is 5. This is 10. So C becomes the controllability matrix. This is 1, 0, minus 1. Minus 1, minus 2, 1. Minus 5, 10, 5. So let's compute the determinant. And we can compute it along the first column. Then we have 0 and minus 1 times. Minus 10 plus 10. This is minus 10. This means that the rank of C is less than 3, which implies that the pair AB is not controllable. This means that we cannot design a pole placement controller because the system is not controllable. But let's see if this can be decomposed into the standard form for a controllable system. Using that, we can design the controller for the controllable subsystem. We can actually check the rank. I think the rank of C is 2. This is going to be the dimension of the to check if it's stabilizable, we'll have to decompose it into the standard form and check if the uncontrollable form is stabilizable. Since the pair AB is not controllable, position. So there are going to be two independent vectors from the controllability matrix because its rank is 2. So we select two linearly independent. So let's select the first one, 1, 0, minus 1. Second. So this is our set of two vectors. Now we need a third column vector so that we can form a transformation matrix which is square and which is also inverted. So first we simplify these two vectors. Simplify it again. So these two are still linearly independent. So let's say the third one could be any of the standard basis vectors in R3. So this could be 1 0 0 0 1 0 or 0 0 1. This is 1 0 minus 1. So observe that this is already a multiple of 0 1 0. So we should not select this one. We select the first one, right? 1 0 0. So let's name this as this is also the controllable subspace because the rank of the controllability matrix is 2. So any linear combination of the two linearly independent vectors from C will span the controllable subspace. And the third vector which you have chosen to form the transformation matrix does not belong to the controllable subspace. This means that 1 0 0 is not a linear combination of the first two vectors 1 0 minus 1 and 0 minus 2 0. Since this is true, then we can find the transformation matrix T, which is simply the three column vectors put together. So how do you check that T is invertible? Calculate this. So this is 1 times 0. And I guess this is 1 times minus 2. This implies that T is invertible. So write down T inverse directly. You can check this later. So you have to sometimes check that if you have to take T or T inverse as the similarity transformation and the other one as the inverse, its inverse. So the T or T inverse which gives the standard form for uncontrollable system would be a transformation matrix. So in this case, you can try by both T and T inverse. I got the answer from T inverse. So this is take T inverse to the similarity transformation. Get the new A bar as T inverse AT instead of T inverse. This is minus 1 6 0 1 minus 4 0 5 0 0 minus 1. R is T inverse B instead of TB. Is it 1 0 0? Okay. So let's see. The controllable subspace is of dimension 2. AC and the uncontrollable state. Then this is BC. So BC has to be 1 0. We got that. This is the pair AC BC is controllable. Dimension of the uncontrollable subspace was minus 2, which is 1. So you get AU as just a scalar. And to check if the system is stabilizable in this case, AU should be negative. So it is negative, right? AU is -1, which implies that the system is stabilizable. So since the whole system is not controllable, we will design the pole placement control for the smaller controllable subsystem. Then transform it to the original system. This is AC minus lambda I equals 0, -1 minus lambda is 4 minus lambda, 6 and 1. This should be 0. So we get lambda plus 1, lambda plus 4 minus 6 equals 0. This comes out to be lambda squared plus 5 lambda plus lambda is minus 6 or plus 6 plus 10 equals 0. So lambda is minus 5. So therefore AC is already a Hurwitz matrix. And let us assume that we want the desired eigenvalues to maybe 10 times to the left of these current eigenvalues. Or let's say maybe 4 times. So this is, let us consider that the desired eigenvalues are minus 5 plus minus j over 15 by 2. And it's 4 times. So it's, the real part is going to be 4 times 5 by 2. This is 10. Or what you can do is just place the eigenvalues and then compare. You can choose only two eigenvalues, so lambda 1d and lambda 2d. Equation. Lambda square plus 5 lambda plus 10. So you can do that. And after that, so you get some k as cleaving creeping, such that AC plus BC times k will have the desired eigenvalues. Only two desired eigenvalues, right? Lambda 1 and lambda 2. And two, so you can only design the controller. Controller can only be designed or the controllable subsystem. Alright, so this was it. We will now move on to the Ackermann's formula. So if you have any doubts, then please let me. Alright, so let's look at another question. This is question 6. Plus 0, 1. So we have already designed the feedback controller using the full placement technique by comparing the desired characteristic equation. Now let's do it with the Ackermann's formula. So the desired characteristic equation is, let's say it has been given to us. This is s squared plus 8s plus 32. So we had some lambda 1 desired and lambda 2 desired. And we computed this. So to use the Ackermann's formula, we need the controllability matrix. So let's say this is going to be B, A, B. So this is full placement using the Ackermann's formula. Okay, 1, 0. So this is simply 0, 1, 1, 0. Here A, B is controllable. So we need to write down the formula. The feedback gain matrix. Is given by k equals. So it's 0, 0 to 1. D inverse dk. So dA is a to the power n plus, let's say, d1. These are the coefficients of the characteristic polynomial. So we already have C. This is a second order system. So C inverse is simply 1 upon determinant of A, 0, 0, and minus 1. It's still equal to 0 and 1, 1, 0. Now we need the polynomial D. So in this case, we have n equals 2, right? So D is going to be A square plus D1A plus D2, identity matrix of size 2 by 2. Let's compute A square 0, 1, 0, 0. So D1A plus D2, identity matrix. D1 and D2 are 8 and 32. So this is 8, this is 32. So we get 8 minus 0, 1, 0, 0. This is 32. This is 8, 0, and 32. Okay, so in this case, K is going to be 0 and then 1. It's a second order system. And we have C inverse, which is C. So this is 0, 1, 1, 0. Then D. So let's see, this is 1, 0. So U is going to be minus Kx. So let's verify. The closed system becomes x dot equals minus bkx. We verify whether the eigenvalues of a minus bk or the characteristic equation is the same as the desired one. If the eigenvalues add eigenvalues, compare the characteristic equation of a minus bk that characteristic equation. Alright, so I hope that this was clear too. Let's look at some more questions on Ackermann's formula. This is to be question 6, question 7. So let's find out the desired characteristic equation. This is plus 1 equals 0. And for pole placement, we need the system to be controllable. And the controllability matrix is also using the Ackermann's formula. So let's compute this. This is B and E. It's going to be minus 1 plus 8. So C is simply 1176. This implies that the pair ED is controlled. C versus 1 upon minus 1. Now we need to find out the polynomial TA. This is going to be for a second order system, this is d1 a square plus d1a plus d2 I2 by 2. So let's compute a square. This is minus 1 8 minus 1 7. So this is going to be minus 7 minus 6. This is 41. This is 48. We know d1 and d2 to be 2. So d looks like minus 7 minus 6, 48, 41 plus 2 times 8. So this is minus 2 minus 2, 16, 14 plus 2, 0, 0. This becomes minus 7 minus 2 plus 2, 48 plus 16, 41 plus 14 plus 2. This is 64. Then this is 64. Then we have 4, 5, 6, 7. Green is going to be like 0, 1. And C inverse. This is minus 6, 7, 1 minus 1. And then D. K equals 0, 1. We get minus 7 plus 8, 64 minus 56. A equals minus 1, 7. So next one is the feedback controller. So let's verify. A minus BK. So A is minus 1, minus 1, 8 and 7. Is 1, 1 times 1, 7. This is 1 and 7, 1 and 7. So let's get the characteristic equation of the closed loop system. This is minus 2 minus s plus 2 equals 0. This is exactly equal to the desired characteristic equation. This was clear to you. Next, I think this is the end for the questions today. If you have any doubts regarding today's tutorial or the assignment, then please go ahead and let me know. We are done with today's questions. All right, if there are no questions, then you are free to leave.